All right. So let's get started. Welcome to the ARC Flux from Space webinar series. So today we have Professor Rhys Parfitt from FSU talking about ARC flux gradients impact on subtropical and mid-latitude weather. Rhys, take it away. Thank you.
Okay, thank you. Just want to share my screen. Okay, there we go. Okay.
Looks good.
Okay. Don't know how to get rid of the oh, right. Okay. Can you still see my screen okay?
Mm-hmm.
Okay, great. Okay, well, thanks for having me. Looking forward to talking about some work, and a lot of this work, I really want to thank my PhD student, Evan Jones, and then also a postdoc, Xiaomi Chakravorty, who I've been working with as well in collaboration with Arno at Imperial College, and then also my collaborators, Ali Wang, Rob Hart, and Bill Dewar, who are all here at FSU with me. So today I'd like to talk a little bit about flux gradients, or the sort of lesser considered cousin of just air sea heat fluxes, and the impact of gradients, specifically on weather in the subtropics and in the mid-latitudes. Okay, cool. Okay, so I'll just do the sort of standard introduction that we all know, that there are certain regions of the world where we have extremely large air sea heat fluxes, and we know that those particular regions are very important for sort of local climate, general heat transport in the atmosphere, and also weather development. Whoops, sorry. Okay, and obviously we know as well that in those particular regions, they happen to coincide with boundary currents, at least in the northern hemisphere. And there's a very noticeable imprint in the time mean of fluxes of the ocean currents, and these sort of large fluxes that are related to sort of ocean variability. Sorry, my computer is self-scrolling for some reason. I'm not quite sure why. Imprint on time mean fields in the atmosphere as well. So we see where we get extremely large time mean heat fluxes. We also get imprints on time mean precipitation. We also find that these happen to be regions where the atmosphere is frequently unstable to deep atmospheric convection. So this particular figure is a percentage on the axis. So the metric they use shows that in that particular region, that at least over the Gulf Stream, for example, that the atmosphere is potentially unstable sort of 50% of the time. And that obviously allows a pathway from the surface up to all the way up to the tropopause. And also these particular regions in the northern hemisphere are regions where we find the most extreme weather development in the mid-latitudes. So obviously we're familiar with the storm tracks, but if you look specifically at where you most frequently get bombs, which are the most sort of rapid deepening of mid-latitude cyclones, those are pretty much exclusively centered on these high heat flux regions over the boundary currents. Okay, so there's many sort of questions about sort of what the fluxes are doing and how they influence the weather systems. And there's a lot of open questions about the mechanisms. So, for example, one particular question is, are the fluxes important, most important because of the direct impact they have, or is it mostly because of the preconditioning of the atmosphere before the weather development occurs? So I've just picked an example of a weather feature in the mid-latitudes, these so-called warm conveyor belts. And so you can kind of see, so warm conveyor belts are these sort of regions or airflows that very rapidly ascend up to all the way up to the tropopause, and then sort of move very quickly away. So this is a particular example, a sixth 6-day back trajectories from some parcels over here in Europe. And basically the black dots are 24 hours apart. So this is a particular warm conveyor belt that was associated with the mid-latitude cyclone that you can see here. So you can see within a day, they make their way all the way up to the top of the, close to the tropopause, and within a couple of days they're all the way on the other side of the North Atlantic in this particular case. So these particular features are sort of cousins of atmospheric rivers. They're sort of, a lot of the features overlap. They're not exactly the same, but in a lot of ways they are. Warm conveyor belts specifically come out of warm sectors of mid-latitude cyclones. And obviously you can think about this direct impact versus preconditioning question here. So obviously a lot of the moisture that is being drawn in and up into one of these airflows is coming out from the warm sector and from some tropical air. Obviously a lot of moisture that gets taken up too was sort of there from sort of a previous high flux event as well. So in that sense, there's some sort of preconditioning. And also prior to the mid-latitude cyclone moving through, there is some preconditioning of the surface baroclinicity by flux gradients that you have there. So that's sort of a preconditioning, but then also as the cyclone moves through, there's a direct impact of strong fluxes as well. So it's kind of that question of, which is more important. I put this up just because I like it, this particular one with regards to warm conveyor belts. You can actually track in different seasons the starting positions of warm conveyor belts, and they tend to be pretty much over, whenever you get them, they tend to be pretty much very localized over these boundary current regions as well. But so direct impact versus preconditioning is sort of still kind of an open question. Another sort of question is, well, what's more important, latent heat flux or sensible heat flux? So I've just put here a couple of snapshots of a few systems, and they're in different sort of regions. This one on the left is over the Gulf Stream region. And obviously on any individual day, you don't really, you can kind of still pick out the boundary current a little bit here, but really from day to day, the fluxes are mostly controlled by what the atmospheric variability is. You can see obviously this is a cold front, this blue line here, and then this red one is a warm front, which is bringing warm air behind it. And then I've overlaid the sea level pressure. So this is a mid-latitude cyclone. So the cold front's bringing cold and dry air, so you get a lot of latent heat flux behind it. And then there's a lot of warm, moist air up here, and you actually get flux into the ocean. And obviously, in this particular case, one thing I want to point out over here, this is a sensible heat flux behind a front in a different region, a cold front, that you can see that there's some cold air behind this cold front here that's causing enhanced sensible heat flux out of the ocean. This particular cold front is not associated with a mid-latitude cyclone. So actually, I argue that really this variability is driven by fronts, not by mid-latitude cyclones. But anyway, there's an open question, like, is it the latent heat flux or the sensible heat flux? Now, sort of general thought would be, well, the latent heat flux is larger, and it's kind of more important. But I'm going to try and talk about why sensible heat flux is important, and a lot of that is through the gradient. So obviously you can see here, if you just focus on the cold front, there's an extremely large flux gradient there across the front. Yeah, my argument is going to be that those are quite important, as well as the absolute fluxes. Okay, so why a flux gradient is important in addition to just absolute fluxes? Okay, so this is a nice figure of something called ocean baroclinic adjustment from a Sampe et al. Paper in 2010. And basically it's this sort of argument that you have a strong sea surface temperature gradient. And basically what happens is the fluxes generate a large surface air temperature gradient. And what happens is when a mid-latitude cyclone comes through and you get some poleward heat flux, that destroys the sort of surface baroclinicity, but the western boundary current and the strong sea surface temperature gradients, you get an anomalous air-sea heat exchange, and that allows for that surface baroclinicity to be rebuilt, and in that sense kind of maintaining the storm track. This is kind of something that is associated with a large-scale gradient. So sort of 6 or 7 years ago, during my PhD, I had a look at a similar sort of effect with the flux gradients, but on a much finer scale. So this is something I did a long time ago, where basically we did some sort of experiments where we looked specifically at where you had over the sort of the Gulf Stream in this particular case, where you had strong sea surface temperature gradients in the ocean. But then in the atmosphere, we looked at specifically across the very tightest part of the SST front and had a look at what happened when you had atmospheric fronts that came through. So really strong gradients in the atmosphere, atmospheric temperature gradients overlaying strong sea surface temperature gradients. And we found in our sort of model runs where we were sort of perturbing the SSTs and various other things that there was a strong interaction. And if you change the gradient, you significantly change how that frontal system develops. But sort of more recently, we've been a bit more interested in a sort of analogous case to this ocean variclinic adjustment, but on a fine scale. So this is still the tightest part of the SST front. This is maybe like 100 kilometers. And this idea that when you have an intermediate air temperature above a strong sea surface temperature gradient, that what sort of happens with flux gradients on small scales. So rather than like over here, maybe this is several hundred kilometers, what happens on sort of 50 kilometers or 100 kilometers. There's some anecdotal evidence that sort of the fine scale interactions and the gradients matter. And so you can kind of see that this is just a wintertime climatology of atmospheric fronts at the surface. So you can see the imprint of the ocean currents. So there is sort of anecdotal evidence that basically these sort of fine scale flux gradients and SST gradients do imprint pretty strongly on sort of atmospheric fronts. But the reason sort of things at this scale kind of interested me or do interest me a little bit more is because it's at these sort of finer scales that the regime kind of shifts in these regions from atmospheric forcing to ocean forcing. And so I sort of stole a couple of these nice figures from Howday, who I don't know if he's here, but this is a figure that he produced a little while ago. And you can kind of make some simple arguments for why the small scale stuff is really important. So, for example, here, this is something that I'm sure most of you know anyway, but if you do a correlation between wind speed, surface wind speed and sea surface temperatures, so this is daily wind speed and sea surface temperature, and kind of just do that correlation, you find that you get a negative correlation pretty much everywhere. That sort of implies that, you know, an atmospheric sort of force in the ocean's responding to the atmosphere. And you can think about that from the sort of perspective of the bulk formula. You sort of that implies you increase the wind speed and then you are reducing the SST as a result of enhanced heat flux out of the ocean. No negative correlation is taken to mean the ocean responding to the atmosphere. And then this is another figure that was produced by Howday. And basically you can do the same thing, but you just sort of restrict yourself to looking at smaller scale variability. You can apply a high pass filter to the data, and then you find that the sort of daily correlation, what you get changes. So you all of a sudden get positive correlations in very specific regions, specifically regions where you expect a lot of small scale variability, like the boundary currents and the ocean fronts in the Southern Ocean. And this is taken to mean that, or sort of to imply that the ocean is sort of forcing the atmosphere. And the idea is if you increase the SST, you sort of increase the vertical mix in, you bring momentum down from aloft, and you accelerate the wind speed at the lower levels. So hence you get a positive correlation. So really, depending on what spatial scale you look at the interaction, it sort of whether the atmosphere is driving the interaction or the ocean is driving it. That idea sort of it changes depending on the scale. This is another, continuing on that theme. You can also sort of see it really clearly by simply looking at the covariability between sort of latent heat flux and sea surface temperature, so the so-called Q prime, T prime. So these are daily snapshots from the start of winter 2009 from the Geophora 3 product. And you can have a look at movies of how this sort of Q prime, T prime evolves through time at different scales. So this animation is courtesy of Stu Bishop. And I really like it because you can just see it very clearly. So on the right, you can see the synoptic scale. And it's very, very clear that essentially what you're seeing here is just cold fronts and warm fronts moving through. It depends just where you are in the system, just sort of determines the sign that you get. But then again, if you look at it, well, you just restrict yourself to looking at ocean mesoscales. In this case, this particular movie is less than 500 kilometers. So you don't even need to go that far down to like 100 or something. then it's very, very clearly different. And you see a signal that's basically anchored over the actual Gulf Stream front. And you see similar things in the Kuroshio as well. So yeah, it's very, very clear that at smaller scales, something different is going on, and it's very important because it seems that at those smaller scales, the ocean is really, really driving that interaction. One last thing I guess I'll say about that, just for background's sake, is that you can also sort of have a look at some equations, theoretical equations. So these sort of types of equations hark back to the Francignon and Hasselmann type stuff from the 70s, and then later like Basugli and Battisti in the 90s. But essentially, you can write a coupled set of equations for the temperature of the atmosphere, temperature of the ocean, have a sort of flux term, and then you have add some noise. So that is n. This is stochastic. It can be noise in the atmosphere or noise in the ocean. And basically, what you can do is you can sort of solve those equations in the case where you just have atmospheric noise, and then in the case where you just have ocean noise. Okay, so this NA or NO, you just set each one to 0. And then you have a look at the correlation between what you expect, the lag correlation between the sea surface temperature and the surface heat flux. And then also you can look at the sea surface temperature tendency and the surface heat flux in both regimes. So what you expect theoretically if the atmosphere is driving the interaction is, and I'm just going to focus on the simultaneous correlation so we can move on to other things. But the blue line, you expect the SST surface heat flux correlation simultaneously to be 0, and then the SST tendency correlation with the surface heat flux to be negative. In the ocean-driven case, you expect the SST correlation to be positive and the SST tendency correlation to be negative. So then what you can do is have a look at these sort of types of correlations in climate models where you have a sort of higher, actually, sorry, these two terms are the wrong way around. Okay, so in eddy resolving high resolution simulations, 10 kilometers or parameterized at sort of 100 kilometers. And you can see these are simultaneous correlations. So in the low resolution climate models, you can see in sort of in the subtropics, mid-latitude, you have 0 pretty much for the SST correlation and negative for the sea surface temperature tendency correlation. So that puts you over here. That's a sort of atmospheric regime that's sort of indicating that the atmosphere is driving the interaction. And when you go to higher resolution sort of climate models, you can see actually there are specific regions where the SST correlation becomes quite positive. And in those specific regions, so I'm pointing out the boundary currents in the Northern Hemisphere, here the SST tendency correlation is 0. And so that kind of puts you over here in the ocean-driven regime. So basically you see it in climate models too, that as soon as you can start in these specific regions, when you can actually resolve the smaller scale features, then you really see a difference in what's driving what. And obviously then that's important for many reasons. Okay, so the way that I've sort of been looking at it is fine scale variability, specifically with respect to gradients. So obviously you get eddy variability, so small scale eddies, but also sort of have the impact from the gradient. And actually, I'm going to talk about both. I'm going to talk about the gradient first. So we've done a sort of lot of work to try and expand this idea that flux gradients at very small scales have a significant impact on extreme weather through their impact on fronts. And that's basically the argument is that smaller fine scale SST gradient is really the driver behind strong fine scale flux gradients, and that really is what is impacting sort of things in the atmosphere. So yeah, initially, just as a recap, I had sort of looked at a long time ago during my PhD at sort of atmospheric fronts over ocean fronts, as you can kind of see in this case. But what I'm going to be talking about now is more a situation where you have strong fine scale SST gradient variability, and then a sort of intermediate temperature profile in the atmosphere. So then really that it's the ocean that's going to be driving sort of the temperature gradient formation or frontogenesis in the lower atmosphere. So the case that I'm going to talk about with regards to this today, that we've looked at, or I should say that Evan has looked at, is this particular situation around Hurricane Teddy. So this is Hurricane Teddy came through in 2020, and it was a tropical cyclone that entered the Gulf Stream region and subsequently transitioned into an extratropical cyclone. And what I've plotted here is just the local, so it's just at each particular point what the sensible heat flux gradient is at the surface. So obviously you can pick out Teddy down here, and then basically if you look over the Gulf Stream, there's a very, very clear, sharp, sensible heat flux gradient and this is clearly related to the fine scale SST gradient. And this is just the Gulf Stream that you can see here. So clearly, I mean, anecdotally, you would look at this and be like, okay, that's clearly the ocean that's controlling that anyway, because there's not really any feature in the atmosphere that would cause something to meander like that along the Gulf Stream at that scale. And the idea is, okay, well, as a tropical cyclone comes into the mid-latitudes, what happens is they don't all do it, but a lot of them will develop fronts and change their structure and transition into extratropical cyclones through this process of extratropical transition. And this is a really interesting sort of case, because these are some satellite images of this particular event. And what you can see is that actually Teddy comes into the region, and there's this sort of region, and I'll show some data, more detailed data about this particular front that's hanging around. But this is actually a stationary front that's kind of low level at the surface, that's kind of being anchored there over the Gulf Stream. And what you find actually is that as Teddy moves into the region, the front that ultimately gets picked up and develops into the warm front of the transition storm is actually the front that was loitering around there initially. So basically, I guess the argument is that, well, if you can kind of change some conditions at the surface, or the ocean is in control of this sort of front in some way, then basically the nature of the transition is going to change. So we wanted to test that. And in this sense, it's a preconditioning. So it's basically, the argument would be that fine scale flux gradients in the Gulf Stream region are better preconditioning the atmosphere, such that tropical cyclones can transition a lot more easily when they move into the region. So that's kind of what we wanted to test. Okay, so this is actually from Era 5. This is Hurricane Teddy. So this is just a little movie here, again, courtesy of Evan. This X up here at the top is Hurricane Teddy. And in this sort of right inset, this is the surface frontogenesis. So I'm just going to play it a couple of times. So you can see that basically there's a strong region of surface frontogenesis prior to Teddy moving into the region that's sort of anchored there in the Gulf Stream. And that basically, as Teddy collides into it, that the front gets picked up and ends up getting sort of consumed into the extratropical cyclone that Teddy develops into. This blue line that runs through Hurricane Teddy here is what is this cross section in the rest of the figure is through this blue line. So you can see kind of like how the frontogenesis is evolving with height. And I'm going to just stop it at one more, this location here, if it allows me to stop it. Okay, so for some reason it's not. Okay, I'm just going to hold it here. So you can see that when Teddy actually encounters that front, that the front, this is really kind of contained within the boundary layer. So this is this is surface frontogenesis, and this is very, very strong, but mostly contained within the boundary layer. As you can see from here, the pink is the boundary layer height. Okay, so what we wanted to do was we wanted to test whether if we sort of change the fine scale gradients, whether we affect the front and hence affect the transition. So we ran some WRF simulations starting a week before Teddy crossed the Gulf Stream front. And I will point out that this is actually there are obviously a lot of simulations that have sort of looked at how, ocean conditions affect weather and stuff, but kind of interestingly, there are not that many, or actually a smaller fraction of them, I should say, run them substantially before the system actually comes into the region. A lot of the time that you'll run a weather simulation and then change the fluxes once the sort of system is actually in the region. We wanted to run it from a week before so we could really have that preconditioning impact. And basically these are the perturbations we applied. We applied a bunch of other ones too, which I'll see some results for in a minute. But basically the only thing we changed was the fine scale gradient. So this is SST anomalies. And we basically just worked along the Gulf Stream front and basically applied a smoothing or a sharpening across like 75 kilometers. So that's from this peak to this peak here. So really mesoscale, fine scale. And we smoothed it, and then we sharpened it, and we wanted to basically, we just ran it obviously in a bunch of different sort of ensemble simulations, and just see had a look at what would happen to the transition. Okay, so this is the control here, and again we ran a bunch of them, but I'm just showing the one where we sharpened it at a fine scale and smoothed it at a fine scale. The large here implies that was we kind of the ones where we changed the SFT anomalies the largest, or the perturbation, and obviously as you would expect, that's the one where you see the biggest response. So this is the front just before extratropical transition onset starts. And I don't know if you can maybe see it, but the front itself is actually that Teddy ends up colliding into is much stronger. Actually, the color bar doesn't really do it justice, but it's about 50% stronger, the frontogenesis for the front. And again, the only thing that we've changed between these two experiments is the SST gradient at a fine scale. We haven't done any large scale changing here. And then when you see during extratropical transition, what you see is that when you smooth it, actually the warm front that actually it develops into when Teddy collides with the front and it starts to transition is a lot less developed. And over here, when you sharpen it, actually you find that you have a much more distinct and developed warm front when the transition starts to happen. And so what you can see as well is this is the sharp one, this is the smoother fine scale SST gradient, and this is hours since ET onset. So this is basically when the tropical cyclone begins to complete extratropical transition. How long does it take to actually complete extratropical transition? So every tropical cyclone goes through a period of time where it's kind of undergoing extratropical transition, and then it is defined as completing extratropical transition a certain amount of time later. And that definition, we use the cyclone phase space, which is kind of the meteorologically accepted way of kind of doing that, or has been for a long time. And you can basically see that in the case where you've sharpened the fine scale SST gradient a week before Teddy moves into the region, that actually the transition itself takes about 10 hours less to complete than it does when you have the smoother SST gradient. So really the argument is that, well, when you sharpen that fine scale SST gradient, you significantly affect the frontogenesis prior to Teddy moving into the region. And then basically the front that Hurricane Teddy collides into is sort of more developed and stronger, and that helps the transition complete a lot more quickly. We also did a bunch of other experiments, and all the ones that were smoothed at different slightly different scales and different magnitudes all took longer than the ones that were sharpened. So we did do more than just two. Okay, so basically it seems that preconditioning effect, which is related to the fine scale SST, really seems to be important. And obviously that we changed the fine scale SST gradient, that is affecting the transition and that sort of development of that system through flux gradients. Okay, so through sensible heat flux gradients, and what we think is then affecting the diabatic portion of the frontogenesis at the surface. Okay, so that's just one experiment. So do we see evidence that this is happening, that these flux gradients at fine scales are really important, all the time? So we had a look at it in a couple of different ways. Again, we were looking in error 5. And so what's plotted here is basically we sort of composited the frontal frequency across all tropical cyclones that were undergoing extratropical transition in the North Atlantic and the West Pacific. And then what we did is we centered it on the storms. The composite is centered on the tropical cyclones that are undergoing extratropical transition. And we plotted the warm frontal frequency at sort of the orientation, and then obviously the color is the percent of time it's found there relative to the center of the storm. And these X's that you can see are basically where you're moving outwards from the center of the storm, and at each sort of slice outwards, you're just plotting where the maximum frequency is of those warm fronts within those extratropically transitioning tropical cyclones. And you can see that it's quite different between the North Atlantic and the West Pacific. In the West Pacific, there's this sort of secondary maxima of warm fronts that develop here that I'm sort of hovering over with my mouse. And obviously, if the idea is that that is supposed to be, if there is the frontal development within these systems is heavily related to fine scale SST gradients, then you would think that that maybe would have some relationship to where your fine scale SST gradients are. So what I've plotted underneath is, again, this is a Gulf Stream and this is a Crochet extension over here. And then I've just moved along with longitude. And the X's show where the maximum SST gradient, the latitude of the maximum SST gradient as you move across. And you can see that actually it's quite different in the two basins. And particularly in the West Pacific, you kind of get this secondary, as you move further out, there's this sort of disconnect. Actually, you get one over here too, but over here you kind of have this region where you have sharp SST gradients. And we think that basically what this is showing is that you get this secondary sort of peak in where your warm fronts develop in the West Pacific that is basically mirroring the SST gradient, although where you generally find the maximum SST gradients. So we think there is some relationship there, and we think that's sort of why you kind of get this secondary maxima here in the West Pacific, which you don't get so much in the North Atlantic. So we do think that that's showing up sort of in general. I will point out that there is a similar, there is a paper that came out last year that looked at this particular, that looked at frontal structures for extratropical cyclones, not just tropical cyclones that were extratropically transitioning. This is all extratropical cyclones. And these authors found that there were significant differences climatologically in frontal structures in the North Atlantic versus the West Pacific. And they made the same sort of hypothesis that basically they seem to find that, or their sort of hypothesis was that they were sort of echoing what the boundary currents were doing. So there is sort of more arguments in the literature to suggest or to hypothesize that could be what's going on. We also tried to see if we could see it directly in the SST. So what we did was we had to look at all tropical cyclones that were exotropically transitioning. And what we did is we tried to make sea surface temperature composites for the cases where tropical cyclones start transition but don't complete, and then ones where tropical cyclones start transition and do complete, to see, well, could the SST gradient or the fine scale SST gradient be controlling whether tropical cyclones can actually complete that process or not? And the results kind of mixed. So the sign is what you expect. So you expect in the case where the tropical cyclone manages to complete extratropical transition, that you would have stronger fine scale SST gradients. And in the case where they don't, you would expect to have weaker fine scale SST gradients. And you do actually see that. And there is some, especially in this case, the not successful ones, there is quite a lot of statistical significance, but it's not as clear as we had hoped. And a big part of that is because it's just the sample size in error 5 is we think is sort of hampered by that a little bit. Where if we had a sort of longer data set, I think we would be able to see something a little bit clearer. But there is some evidence that you see that in the SST. So this is a week before, actually. So this is 7 days prior. So in this particular case, where you have tropical cyclones that complete that start extratropical transition, but somehow don't manage to complete in the 7 days leading up to that, you do find that you have statistically significant weaker fine scale SST gradients than you otherwise would. So that is consistent with that. Okay, so what I just talked about on the left, this is really this ocean baroclinic adjustment is this large scale SST gradient, sort of large scale gradients, large scale flux gradients. And then what I'm referring to here specifically is small scale, sort of less than 100 kilometer flux gradients and sea surface temperature gradients. Now, as I mentioned before, those fine scale gradients I'm super interested in because it's really at those scales we see a big sort of regime change where the ocean's really driving the interaction. We also have been looking a little bit at sort of how these large scale sea surface temperature gradients and small scale sea surface temperature gradients, like how related they are. And I won't go into that because I want to get onto the other stuff before I run out of time. But basically what you see down here is a correlation between monthly fine scale or local SST gradient anomalies and large scale SST gradient anomalies. So we just created two indices, one which tracks the large scale SST gradient and one that tracks the fine scale SST gradient on a monthly time scale. over the Gulf Stream. And you can see that there is some relationship, but there's a lot of, it's patchy. And sort of what I sort of take that to mean is you often see a lot of experiments where like the sea surface temperature gradient has kind of been, suggested to be not that important. But if you actually look a little bit closer in a lot of these sort of model experiments, you just blanket apply a filter, or, you're kind of changing both at the same time. So it's really, really difficult to know like what scale we're actually talking about. And most papers that look at sea surface temperature gradients don't specify a scale. It's just, this is the SST gradient and we will change it somehow on some scale. But actually there is some degree of relationship between the different scales, but not as much as one would perhaps think. Okay, so I'll try and speed up a little bit to leave enough time for discussion. But basically, so we have these fine scale gradients impacting individual fronts. We've already shown in the case of extratropical transition that that it seems to impact sort of longer term variability or even the time mean quite a bit. So I'm just the quick argument for why we should care is because it affects individual fronts. It affects the rainfall of individual fronts, these fine scale flux gradients, okay, through the fine scale SST gradients. But if you actually look in the mid-latitudes, sort of especially in higher resolution data, you actually find that, so this is the percentage of precipitation associated with an atmospheric front, and we calculated it in a bunch of different reanalysis products. For some reason, the color bar isn't showing up, but red is basically 80 to 90%. So most of your rainfall in the mid-latitudes is associated in some way, especially in your high resolution products with an atmospheric front. So if you if these small scale flux gradients are significantly changing how sort of these fronts develop, and on longer time scales as well, it's also going to be important for understanding sort of longer term precipitation variability on seasonal time scales or longer. I won't talk about this too much because I'm running out of time. But also you can show that fronts are a significant contributor to the time mean surface convergence as well. So basically, if you have a look at sort of surface wind convergence and then vertical motion and communication from the surface to the troposphere, to the tropopause, then fronts have a really significant role in setting the longer term variability in that too. So basically, I am trying to argue that this particular interaction doesn't just affect individual weather systems and individual fronts, but it affects much longer term variability, has important implications for seasonal and longer variability in winds and also in precipitation. So last few quick things that I wanted to talk about is, so far I've talked about fine scale SST gradients. Obviously in these regions there's a lot of eddies as well, a lot of eddy variability. And I think most people accept now that eddies, seem to imprint quite a bit on the atmosphere. It's a really famous paper from Frenger that came out 10 years ago where they identified a bunch of eddies. I think this was in the Southern Ocean. And basically they showed that they did composites of the SST and then the wind and the rain rate. And you can see that over the eddies, you very clearly have an increase, or the warm eddies, you have an increase in the wind speed and then the associated rain. And sort of the conclusion from this particular paper was that basically you have sort of that sort of warmer region of water, and that drives an enhanced vertical mix-in, and you basically then can generate more rain as a result. But what I wanted to sort of argue or kind of show briefly is that actually I don't agree with that particular sort of schematic, that the eddies are directly driving the rainfall, and mainly the simple argument for that is from what I just showed before, that actually most of the rainfall happens through fronts. And so we wanted to just quantify that and show that. So there's some other work that we've done where we have an eddy resolving 24-member MIT GCM ocean circulation ocean circulation model or ensemble, and that each member is 50 years. And so basically what we wanted to do was we wanted to take sort of the SSTs from 3 or 4 of those ensemble members, and we wanted to use those SSTs to force force a month of atmospheric variability in WRF. And so we chose February 2009, I think, or February 2010. And basically, we basically just ran a 1 month simulation of that particular month, but the SSTs were from slightly different ensemble members. So basically, it's supposed to have a look at what the atmospheric response to intrinsic ocean variability in the Gulf Stream region is, as represented by the SST, different SSTs from those models. So in this particular case on the left, this is just an example of one of the ensemble member SSTs minus the ensemble mean. We did like, this is just 3 or 4 simulations. So this is the anomalies in one of the simulations from the 4 ensemble mean. And so you can see that there's some eddy variability and some intrinsic variability. What's really interesting is that if you have a look at the difference between the simulation forced with the SST from ensemble member 1 and minus it from the 4 simulation mean, then basically you see that even after a month, that there's a very, so that the color is the SST again, as you can see, and then the contours are the rainfall anomalies. And you can see that you only actually need to run it a month for you to be able to see an atmospheric response to the intrinsic variability. You can see that they're pretty well correlated here with stronger SSTs, co-located with positive rainfall anomalies. It's even more striking. You can also have a look at the heat flux too. There's a very clear relationship there between the intrinsic SST variability and the heat fluxes that are generated in the WRF simulations. So really, even after a month, you see the imprint of the intrinsic variability and this sort of smaller scale variability. This is actually along this white line in this figure from this particular simulation. This is just the dots of the sea surface temperature anomalies, and the blue line is the rainfall anomalies. So you can see that they line up pretty well for the most part. But the one thing that I really wanted to point out is that you can have a look at how much of these rainfall anomalies in the simulations are associated with fronts and associated with outside of fronts. And admittedly, I haven't included enough information in this figure, but basically the sort of black that you see on this bottom right figure is where the rainfall is, or rainfall anomalies are, and then the color is basically where you get some frontal frequency, and this is time here, and then this is longitude. But long story short, basically, when you do this particular set of experiments, you find that like 90% of the rainfall anomalies that are responding to this intrinsic variability are basically frontal. So what that means is that when you have sort of like eddy variability, that what it seems to be happening is that the eddies are injecting more moisture into the atmosphere, but actually for the rainfall to occur, you need a front to come through. So that's kind of a different picture than eddies directly just forcing like a fountain of rain, you know. So that's again another fronts are important for eddy variability as well. So this is fine scale variability, not just all fine scale variability, including sort of eddies, not just the fine scale SST gradient. Okay, so the last thing, I'll try and wrap this up in the next sort of like 3 or 4 minutes, that I've sort of been thinking about is that I've tried to hopefully at least somewhat convince you that the fine scale SST gradients and fine scale flux gradients as a result are really important, not just for subtropical sort of extratropical transition, but mid-latitude fronts and cyclones, but also for longer term variability. And that's because you impact the fronts, you also then by definition you impact the seasonal and time mean winds and rainfall as well. So really these flux gradients are important for all time scales. So then the question is, well, you know, how well do we actually represent these in data sets or in models? So I was sort of playing around with this at the end of last year and kind of got a bit distracted, but trying to finish the work now. I was just curious in certain data sets, like what the flux variability surrounding fronts are and the flux gradients. So this is error 5, winter time. I just picked a location down here and just said, okay, whenever I have a cold or a warm front, so cold is blue, warm is red, sort of what is the lead lag sort of flux variability? So these are just flux composites centered on cold fronts. So obviously, when you have a cold front come into the region, you get a big increase, as you would expect. This is latent heat flux. Warm front come into the region, you get a decrease in latent heat flux, as you would expect. You see the same thing with sensible heat flux. So again, same region, big increase when a cold front comes by, decrease when a warm front comes by. But this is a composite. Individual events are much stronger. So this is a composite over many events, this central figure. The bottom figure is just through time. So the blue lines are where you get cold fronts and red is where you get warm. You can see that you get increases after cold fronts and decreases after warm fronts. You can see that individual events can be much bigger. Here you go from sort of 10 watts per meter squared up to about 200. So that's massive. So I was interested to look at the distribution. So basically you can look within 24-hour window of a front. The top line is basically what is the absolute latent or sensible heat flux change when a cold or warm front passes. So blue is cold and red is warm. It's all positive, but basically where you see blue, that means a heat flux increase, and then red, the associated, it's a heat flux decrease. Hence why the sort of axis is increase, decrease. So you can see that really your median change in latent heat flux, for example, when a cold front passes or a warm front passes, is a change of about 200. And this is in a 24-hour window, right? So the changes are quite large in quite a short amount of time. If you calculate it as a percentage change, actually, and obviously there's some really large values, because sometimes you can have sensible latent heat flux is close to 0. So when you calculate the percentage, it's really, really large. But the point is that basically within a 24-hour window, when one of these fronts passes, or whenever you have a strong surface temperature gradient that may get identified as a front, you get 200 to 300% changes extremely regularly in latent or sensible heat flux, and then more quite often. So one of the things that I've kind of been curious about, and I'm by no means an expert on it, so I'd be curious to see what people have to say, but basically a lot of satellite-derived products sort of bin variables over windows of time. When they calculate fluxes, they'll sort of bin the variables they need. And I sort of wonder that, so I've seen some of these products that will calculate fluxes based on variables within sort of like a 3-hour window or a 6-hour window or something like that. And I sort of wonder that the accuracy of that when you find such large changes within a day, sort of how, I wonder if this is a sort of a flux variability surrounding fronts is something that just doesn't exist basically in flux products. And I'll move through this quickly because I'm running out of time. But basically, like, you can look at observations of like ship tracks with what the actual fluxes are, and the gradients all seem to be quite off, and a bunch of different reasons for that. Again, when you have products, there are difference in techniques for estimating the parameters. There's different spatial resolutions in the variables. But then this is the one that I'm sort of more interested to discuss, is basically that inputs for the calculations come from different satellites with different overpass times. So that was actually a main motivation behind the butterfly mission, which was, well, we need simultaneous measurements of all the variables we need, because if we don't, then we're not getting accuracy here at all. This is a sail drone that was from Diard et al. Over the Gulf Stream, and they compare the sensible heat flux with Error 5. And there are really large disagreements in flux gradients surrounding fronts. That's like the most noticeable discrepancy. So an analysis of that would be useful. And I guess my open question that I'll lead with is, I've hopefully argued that flux gradients are really important for the development of subtropical and mid-latitude weather, extreme weather as well, and both at fine scales and large scales. It's particularly important at small scales for atmospheric fronts, because you have massive changes in air-sea heat fluxes that occur extremely rapidly. At these small scales, we have ocean-driven regimes emerge, and these are unresolved in many climate models and data sets. But this is kind of the one I wanted to discuss, is that, I've hopefully argued reasonably well that the small-scale flux gradients are quite important, but there's seemingly no way of validating them, just because I personally don't know of a flux product that has any sort of reasonable spatial extent where we could look at these interactions, because you need, the appropriate spatial resolution, but also simultaneous measurements. If you bin, you could end up binning across a front, and then you just lose the gradient completely. And then basically, I've just end the talk with some projects that I'm working on that I just want to thank NOAA, NSF, and NASA for sponsoring some of this work. Okay, so that's it. I'm really sorry that I went over time a little bit.
No worries. Thank you so much, Rhys, for the very comprehensive presentation. And in fact, your results have been quite important for the development of the mission concept for Butterfly. So the floor is open for questions. If you have questions, feel free to raise your hand or unmute to speak or put in the chat. So while people are thinking about questions, oh, Sarah.
Yeah, this is great, Rhys. I wondered, you talked about the Northern Hemisphere, and in passing, your initial plots showed the Southern Hemisphere looking really different. Is it actually different in the Southern Hemisphere, or was that just seasonal effects?
Southern Hemisphere in terms of
fronts, prevalence of strong heat fluxes across fronts.
Yeah, well, the heat fluxes obviously tend to be in the time mean anyway, they're a lot weaker in the Southern Hemisphere. But actually specifically across these particular regions, like where you have strong SST gradients, the flux gradients can often be just as large. And actually it's an interesting question that I get a lot, and I keep saying that I'm going to look in the Southern Hemisphere, and I really should. But you know, we've looked briefly at similar sort of things in the Southern Hemisphere, and our conclusions don't change at all. Actually, when you have a look at the like fluxes in and around sort of frontal systems, they can be just as large, and the gradients are just as large. So I don't expect there to be any significant difference. Really expect it to be just the same in the Southern Hemisphere.
So from a process scale, that you expect to see the same things.
Yeah, absolutely.
But from a climatological mean, it looks a little different.
Yeah. Yeah.
Cool. Thank you.
And Megan has a comment in the chat.
Yeah. Thanks, Rhys. That was super interesting and great to see all of that work. I just want to point out that Tomoki Tezuka has a set of papers showing how the importance of also considering the corresponding fronts in mixed layer depth, because there's some cases where, you know, as you are losing heat flux or is losing heat on the warm side, you might think that that would be flattening out the sea surface temperature front. But if the mixed layer depth is really thick on that warm side of the front, then in fact, the cooling on the cool side might be much stronger. And that could lead to a sharpening of the front, even in the case where the ocean is projecting and enhancing the front in the atmosphere. And so that can lead to a positive feedback that can, between the ocean and the atmosphere, that could lead to persistent influences.
Yeah, so that's really I'm familiar with those papers, and I think that they're really interesting. Obviously, I've kind of mostly been focused today on just the atmospheric side, and I haven't really talked about sort of those feedbacks or sort of coupled effects as much. I've really just kind of been considering, well, what is the atmospheric response? But obviously, in terms of flux gradients, you're absolutely right that it's the same sort of thing, that there are really important processes that occur. So I've talked about one, which is simply just, you know, flux gradients and how they influence temperature gradients in the atmosphere. But obviously, as you mentioned, that you know, conventional thought is that we have a big cold front, lots of heat flux, then you will aim to sort of to damp that sort of front in the ocean. But there are certain times of year, I think there's like a couple of different times a year where where you get frontogenesis in the ocean, and you strengthen that front because of the mixed layer depth variability. So obviously, again, that's kind of one of those things that's important because, as you said, that's an important coupled feedback. And obviously, again, it's the same kind of argument, though, that flux gradients are important for that. Obviously, how the flux is changing over sort of relatively short region. But again, it kind of comes to this thing that I sort of wonder if we're really in a position where, well, I personally don't really know, like when I think about some of the model stuff or looking in reanalyses, I kind of think to myself, how can I validate these flux gradients? And obviously that find it a bit crazy that, people, really when we think about heat fluxes, we'll we're blending in data from all these different sources. And so again, it just, what you're saying is, again, another example of where why these flux gradients
role of vertical flux distribution, which is typically in the boundary layer, in frontogenesis.
Where's that?
So one up. Oh, there are several more, actually. So Rick, Megan, and then Hervey.
Oh, okay. Yeah, so
Yes,
that's a good question. I don't have an answer to that, actually. I don't know. We've really just touched the surface of how these fronts are being developed. Actually, one of the projects I mentioned at the end there is trying to understand a little bit better how flux variability at the surface impacts the vertical distribution of the front. So far, we've really only looked at or identified fronts at 900 at sort of one level. But obviously, it's important to know what the vertical, how it vertically affects the vertical structure of the front, because that's also going to affect how rainfall and other things like that. So yeah, I mean, it's a great question, and unfortunately, I don't know the answer, but it's something that we're looking at now, how the vertical structures are affected. As I said, I've just kind of looked at things at 900, unfortunately. I'm not quite sure.
okay, thank you.
So we are at the top of the hour. So let's thank Rhys again for the presentation. For those who want to stay and continue to ask questions, I'm not sure if Rhys need to go or not.
I can stay for a little bit if anybody's interested.
Okay, yeah, for a couple of minutes, if you could. Yeah, for those who need to leave, please feel free. And then there is another question by Rick. Rick, I'm not sure if you need to go or not. You really want to ask your question, or is it a comment?
Hi, can you hear me? It's more of a kind of an interest in lack of study of the cyclone that happened, or if you're reaching into the preconditioning by previous cyclones, this sort of question isn't really very much in the literature yet, and it's perhaps a topical one. But what is the relationship of families of cyclones and small groups of cyclones? Or perhaps what came up in previous talks in this seminar series is the possible role of mixing by small vortices that are hard to capture along these ocean frontal regions.
Yeah, I mean, that's so a couple of thoughts on that. It's a great comment. Obviously it is possible that we're not seeing or we're hampered in the statistical significance looking at the 7-day SST because we're you know, it's being conflated with events that we're not interested in, right? So obviously you get multiple cold fronts a lot. So you can have 2 or 3 cold fronts, you know, if you're just looking at, say, SST signatures to, you know, individual fronts. In the case that we were looking at with tropical cyclones as well, though, actually, it's true that in that case with Teddy, there was an extratropical cyclone that had made its way through sort of just a week prior. So it's possible that, you know, that there is some confusion conflation there in the composite. So that's a very good comment, and one that actually it would be good to try and filter out. But yeah, also I think, you know, it's I again, it's kind of like I was sort of mentioning at the beginning, that the role of sort of a series of cyclones actually hasn't really been considered that much. I think typically, if you took like 100 papers looking at, say, you change Gulf Stream SSTs, for example, how do they affect weather development? The vast majority of them will sort of play around with the SSTs sort of several days before one individual storm moves into the region. But obviously, as you mentioned, we know that a previous cyclone is very, very important for the characteristics of the next one coming through. I mean, a simple way to think about that is just your biggest fluxes, or ocean to atmosphere evaporation and heat and moisture flux, comes behind the cold front. So a lot of that obviously you get like sort of local convection, but a lot of that moisture sticks around for the next front to come through and take up. So that alone is going to be a cyclone that was happening previously, and the fluxes sort of there are going to impact the next system that comes through. So as you say, like that sort of thinking about it in terms of families of cyclones, I don't really know much of that stuff in the literature, and it would be a really interesting thing to look at. But there's certainly a lot of evidence to suggest that that's something that we should do.
And Odyssey and Butterfly would both potentially contribute to our observations of the intervening periods between these high energetic events, for example, if that was what was of interest.
Yeah, absolutely. I think, I mean, it's obviously important anyway. I mean, that's kind of why at the beginning I was trying to say that the preconditioning is really, really important. So it's quite in sort of, you can kind of think it's quite easy to visualize, or when you have a really strong temperature gradient in the atmosphere, clearly the fluxes are going to be very different on either side. But I think what I was also trying to argue is that even in the absence of a strong temperature gradient in the atmosphere, there are certain regions that are very important climatically and for weather development, where you get really, really large flux gradients regardless. And at smaller scales, they're really controlled by what the ocean is doing. And so you really need to be able to resolve those as well. And again, as I was kind of saying, that these things happen on such small scales spatially that you need the spatial resolution to do it. But one of the things that I'm personally most excited about with Butterfly is the idea that we would have temporal consistency as well, which is something that I think is not talked about enough. I think a lot of the time we tend to want to go higher spatial resolution. But a lot of the higher spatial resolution products still, you know, assimilate within a temporal window. And when you have very fast moving features at small scales, you're missing a lot of the interaction. So that's another reason I'm very excited about Butterfly.
Okay, thanks.
That's a very good point.
Great talk.
Yep. And that's also a good note to conclude the webinar. Thank you so much again, Rhys, and take care, everyone. Bye-bye.